Okay, so I'm going to go over this first exam. First question, find the x and y intercepts of the graph of each function if they exist. So y equals 2. If we picture that, that's just a horizontal line. And so a horizontal line is not going to ever cross the x-axis, assuming it's not the x-axis itself, which is not. It's 2 units above the x-axis. So no x-intercept. Of course, that'll cross at y equals 2 because every y value for any x value on that line is always 2. On the second one here, let's see, okay. On the second one here, we have x squared minus 4. So if we set y equal to 0 to find the x-intercept, we can solve and we get x equals plus or minus 2. Now I want to point out something here. Once you got to the step 4 equals x squared, a lot of people took the square root, which is correct. When you take the square root of both sides, you need to put plus and minus there. I had made a video of this before. There's some confusion. Take a look right here at this square root. This is not a plus or minus. This is only the positive square root. If there's no sign out front, it's called the principal square root, which is positive. In other words, if we had square root of 9, that would only be equal to 3, not negative 3. But when we take the square root of both sides, we need to take the positive square root and also the negative square root. So that's why we get this. That was a common misperception. And of course, if we put 0 in for x, we get y equals negative 4. C, pretty simple substitutions there. Number 2, looking for the domain, we're worried about a couple things here. One, we want to make sure that this x does not equal 0. So that's why I put that here. 2, we want to make sure that this is not a negative number. Now it is okay if it's 0, but we need 3 minus 1 over x to be greater than or equal to 0, which is what I've written right here. So notice I can add 1 over x to both sides. Adding does not change the sign. We only change the direction if it's multiplying or dividing by a negative. So here's where we get into a little issue. If x is greater than 0, when we multiply both sides by x, we don't change the sign because x is positive. So this is this situation. And then we can just divide both sides by 3. So if x is a positive number, it's got to be greater than or equal to 1/3. Now we could also have x as a negative number. If x is a negative number, notice that no matter what number it is, 1 over a negative number will be negative, and then will be less than 3. So that'll always be true. So x is either a negative number up until 0, cannot have 0, or it's 1/3 or higher if it is a positive number. So we're unioning those two parts of the domain. Okay, number 3, just a lot of messy algebra. Most things cancel when you get to the end. Notice that we divide top and bottom by h, meaning that every term gets divided by h, and that gives us 4x plus 2h. This is a precursor to derivatives that you'll get into if you do take calculus. Okay, slope-intercept form. We're just setting up the slope to get slope to get negative 2/7. Once we get that, several different ways we could do it, but I just used the form y equals mx plus b, plugged our slope in, plugged an x and y coordinate pair, could have plugged either one in, doesn't matter, get my intercept, and then write it out. Solving the inequality, again, different ways to do it. I prefer to get everything over on one side, make it an equality, not an inequality. That's what these equal signs are, because then I can solve it directly, find that x is negative 9 and 1, and once I find those critical points, then I just have to figure out, okay, what does this graph actually look like? I know that this is a parabola and it's opening up, because the coefficient of the x squared is positive. So it's going to look something like this if these are the two x-intercepts. And since I need, basically I can subtract 9 here, since I need that parabola to be greater than or equal to 0, I'm talking about the two parts of the parabola that are above 0. The y values are above 0. So that's everything before -9, including -9, because we have this equals there. And then everything from 1 on, from x values of 1 and higher. Okay, this transformation, a couple different ways. You could do it analytically, noticing that this -1 will drop the graph down 1, this x plus 1 will take it 1 to the left, and this 1/2 will do a vertical compression of 1/2, so it'll squeeze it together basically. Or you could just set up the method that was used in the book, which basically works backwards to end up with the new set of points. Okay, here's a key. Give an example of a quadratic function. So first of all, what is a quadratic? A quadratic is going to have an x squared term. That's going to be the highest power of x. And so I think a lot of people missed that point. No real roots. So for example, some people put the line y equals 2, like you had in problem number 1 on the exam. That graph, the graph of that function, does not ever intersect the x-intercept. That function has no real roots, but that's not a quadratic function. Y equals 2 is not a quadratic. Here we have y equals x squared plus 1, because I know that my basic parabola will touch the x-axis in just one place, and then I'm doing a vertical shift, so it basically lifts it up off that x-axis and never touches. You could have plus anything there. You could shift it left or right as long as it was above, or you could actually make it a negative x squared minus 1, so put it opening down and then shift it below the x-axis. That would have been fine. One real root, y equals x squared, so this is just that basic parabola that touches down at x equals 0, y equals 0, so it has its vertex at the origin. Two real roots, here I'm just pulling the standard parabola down 1 so that it will now hit the x-axis twice and have 2 roots. Okay, 8, I'd like to point out there's lots of different ways to do this. I'm just going to show you one way. Because we know where the roots are, I would start with that because that's an exact thing. There has to be a point here. The function has to intersect the x-axis at -1/2 and at 3 because those are roots. At increasing on -4, 0, so I'm just starting and going up. Now, it says also increasing on 0, 3. So either I'm increasing on this entire thing or I have a break at 0. Both of these are possible. Now here I just put real roots at these two values. So I guess you could have, well, no, I guess you couldn't have. So if we continue to increase from x equals -1/2, we're going to go above the x-axis. So by the time we get to x equals 0, we cannot have a root there. And so there's no way we would continue to increase that entire way till we get to x equals 3 and still have a root at x equals 3. So that's why I went ahead and created a jump discontinuity here at x equals 0. So it still is increasing on this section and on this section, but we wouldn't say that it's increasing on the domain -4 to 3. Okay, and then we do need to be decreasing, so that's why I dropped it. We also have to have an absolute minimum at x equals 0. So when I come up here for this, I just want to make sure that this point is lower than anything over here and anything over here. Putting this in standard form involves completing the square, which is what I do right here. vertex and axis of symmetry. Once I've put it in standard form, the advantage is now I can just pull out whatever is being subtracted from x is the x value of my vertex. Whatever is being added to this perfect square is my y term. So I have 1 and -9. Axis of symmetry on a standard parabola will always line up with my x value of the vertex. The vertex will always be on the axis of symmetry. And then we can say where it's increasing, decreasing. I think most people got that. Minimum, and here's the more technical reason why, because we know that it's decreasing on this interval, and then it's increasing on this interval. So because of that, f of 1 is less than or equal to f of x for any value of x that we could plug into the function. Okay, finding the real zeros. First, I would strongly recommend factoring. So once I pull out that x squared, I notice, oh hey, now I could use the quadratic formula for this. It turns out it factors nicely. So I get this situation where I have this polynomial into 3 factors, although one of the factors is repeated here, this x squared. So because of that, we say that x equals 0 is a root with multiplicity 2. Then just solving these others, setting them equal to 0, we get 2 more roots. Each of them just appear once in the factored polynomial. And some of you tried to use short division, long division. That would be fine. You still need to find a root, first of all. Once you find a root, then you can use long division to break the polynomial into 2 separate factors. Now you could use long division to try to find the roots too, but that would be pretty laborious. It's better to just take your set of roots and plug it into the original equation, see if you end up with 0. But of course, all of that we didn't have to do in this case because it factored out nicely. Okay, you can't read that real well, but we have f of x equals -x squared. Now you could create a chart and put a bunch of x values, figure out their y values, or you could realize this is just the standard parabola, which would be something like this, and it's flipped upside down. Same for g of x equals absolute value of x minus 2. So the absolute value of x is this perfect V shape, but we have it dropped 2. The y value drops 2, so we shift it down 2, or completely fine to create a table of values and figure out where that graph is. The nice thing about sketching these graphs then, we can figure out when f of x is less than or equal to g of x. So we know we have this parabola opening down, and we have this other absolute value graph up until the intersection. So for any x values less than or equal to the intersection, f is going to be less than or equal to g. Any values past the intersection, x values greater than whatever that intersection point is, also the parabola, the f function, is going to be less than or equal to the g function. So the only thing we have to do then is find the intersection points, and if you created the table nicely, you may be able to find it. You might be able to take a guess and plug them in, or you could set these 2 functions equal to each other and solve them. When you do that, you'll have to create 2 situations, positive x and negative x, and that's how you'll get these 2 separate intersection points. Okay, we have a polynomial here that's already factored on us, which makes our life very easy. Degree, we're just looking at all the different powers of x. You may even want to look at the leading term first, because then that'll show you that the degree here is 4. But the power of x here is, the highest power of x is going to be 4. The leading term, we just multiply all the different x terms, and we get 2x to the 4th, so that's going to be our leading term. And constant term, we're just multiplying all these constants, the -2, the -1, the +2, and the -1, and that'll end up with -4. End behavior, we're plugging in as this gets lower and lower towards negative infinity. We can really just look at the leading term there. Plug a large number in there. Either way, this fourth power will make it positive, and we'll go to positive infinity.